Hello and welcome to the Further Maths Support Programme revision recordings for A-level modules. Today we're going to be looking at Edexcel Mechanics 2, and this is the first part of the Edexcel Mechanics 2 sessions. There are going to be 5 of them altogether. You can see that here the first one is going to be projectiles. If you're interested in any of the other topics that are listed here, you should find that recordings are available for those on the same site as this one. So let's take a look at the specification for projectiles for Edexcel M2. You can see here that you need to be experienced with motion in a vertical plane with constant acceleration, e.g. under gravity. It says here e.g., but I've never seen any systems where the constant acceleration in the vertical plane was due to anything other than gravity. You also need to be confident on simple cases of motion of a projectile. Simple here means that there's going to be no resistance due to air resistance or friction, and also you won't need to deal with bouncing off slopes, etc. Okay, to handle projectiles questions you need to be absolutely confident with your constant acceleration equations. I've listed them here on the left hand side. I've also listed a simplified version here, S equals ut, which is used in the horizontal direction where there is no acceleration component. And this is really the nub of the projectiles method, separating out the horizontal component from the vertical component. You can see here below the diagram that I've given expressions for the horizontal displacement at time t and the vertical displacement at time t. And I just wanted to have a little moment to mention about directions here. This particular example that I've shown here shows the initial velocity having an upward positive component and the gravitational acceleration downwards, g here being in the downward direction. For this reason, if we take the initial velocity, in this case u sine theta in the upward direction as positive, then the acceleration due to gravity must be negative, so we end up with this negative value in here. And it's important to make sure that acceleration due to gravity is always in the downward direction relative to whichever direction you've taken for your initial velocity. Okay, so let's take a look at an example. If you're playing along at home and would like to work this question through before I go through the solution, then now is a good time to pause as I'm going to start the explanation. Okay, so the particle's projected from a point O with a speed u at an angle of elevation of alpha above the horizontal and moves freely under gravity. So I'm going to draw at least the first part of that diagram. So we're projecting at speed u at an angle alpha to the horizontal, and at time t I'm going to say that it's reached this point x, y. That means that the horizontal distance it's travelled is x and the vertical distance it's travelled is y. Just notice here that they've used lowercase u as the initial speed. Do be careful with this when you're using your SUVAT equations. Lowercase u is the initial velocity in whichever direction you're considering. So when, for example, you use s equals ut in the horizontal direction here, you need to remember that lowercase u there is the horizontal component of the initial velocity. So in this particular case that's going to be u cos alpha, and we're going to use that now. I just want you to note that the equation we're looking for here, that we're trying to show, involves no t. And this is a feature of the very useful fact that t, the variable for time, is the same in both directions. Everything else is different. The acceleration is different, velocities are different, displacements are different in the horizontal and vertical directions, but the time ties both the horizontal and vertical directions together, and that's the key to answering this question. So we're going to look first of all in the horizontal direction. If we use s equals ut in the horizontal direction, I'm going to put this in inverted commas just to make sure that we don't fall into that trap of using the wrong u here. So s equals ut in the horizontal direction, that means that x, displacement in the horizontal direction, is going to be u cos alpha multiplied by t. I'm just going to rearrange that to get an expression for t, so I know that t equals x over u cos alpha. I'm going to use that in a minute to substitute into my vertical calculation. Okay, so here's my vertical calculation. Again in this direction I'm going to use s equals ut plus half at squared. This time we need to use a version with an acceleration because it is being accelerated by its weight. By its mass, by its weight, I was right the first time. Okay, so in the vertical direction the displacement is y, and I've taken upwards here as the positive direction, so my initial speed in the upward direction is going to be u sine alpha multiplied by t, that's s equals ut, done. Now minus half g, this is because the acceleration, a in this case, is going to be g meters per second squared downwards, and that's in the opposite direction that I've assumed to be positive, so making it negative. So that's plus half at squared replaced by minus half gt squared in my particular calculation. And now I've got something I can take my expression for t and substitute in here. So y equals u sine alpha multiplied by t, which is x over u cos alpha, minus half g, and my t squared becomes x squared over u squared cos squared alpha. You can do a little simplifying here. The initial u's will cancel. Sine alpha over cosine alpha becomes tan alpha. So that gives me my x tan alpha minus gx squared. That half becomes a 2 in the denominator. 2u squared cosine squared alpha, which is what they required in the first place. Okay, again let's take a look at the second part of this same question. If you're playing along at home, if you'd like to pause now, I'm just about to start through the explanation. So I'm going to start with a diagram here. So the object is thrown from the top of the cliff with a speed 7 meters per second at an angle of 45 to the horizontal, and the cliff is 8 meters high. Please excuse my diagram is really a bit too small, but I hope you won't mind too much. Okay, so that's my that diagram there. I'm asked to find the horizontal distance of the ball from A, this is the point A, when the ball is 1 meter above the beach. Excuse me a second. So 1 meter here. I'm trying to find this horizontal distance here, which I'm going to call D. Now, we have an equation here that connects together the horizontal and vertical distances. So I'm going to use that equation, I'm going to substitute into there. Y is going to be minus 7. Just check why that is. It starts here at A, and it's actually dropping through 7 meters of distance to get to the point that we're thinking about. So y is going to be minus 7. X is the value we're looking for, which I'm calling D here. Tan alpha, that's going to be tan 45, which we should be able to tell quickly is the same as 1. We'll deal with that in a second. GD squared, substituting in here, over 2. U squared is going to be 7 squared, which is 49. Cos squared 45. Okay, so I think you can see here that we're starting to develop a little quadratic equation. Let's put some more tidying up in there. Minus 7 is D. Tan 45 is just 1. Minus 9.8 D squared over 2 times 49. Cosine of 45 is 1 over root 2, so cos squared is 1 over 2. So I'm just going to put a times 2 on the top line here. I think there's some cancelling you can see. We can cancel those 2's. We'll do a little bit of multiplying up. I think that gives us a quadratic that looks something like this. D squared minus 5D minus 35 is 0. That's the quadratic that comes out of it. If we use the formula to solve that, I think it doesn't come out exact, so we're going to go formula. D equals minus B is 5. Now we'd normally have a plus minus in here. Excuse me, I'm just going to mute my microphone for a second. Sorry about that. But we know that D's got to be positive, so we're actually going to take only the positive version in here. So 5 plus or minus square root of B squared minus 4AC. That's become a positive because 35 is negative in our equation, all over 2. And if you pop that into your calculator, I think that gives you a value of 8.92 meters. And that feels about right in terms of the horizontal distance travelled. 8.92 seems like a reasonable amount. That's just the 3 significant figures. Okay, so that's our first part there. We're then going to go on and have a look at this next bit. Boy's standing at B, which is vertically below A, just here. He starts to run towards where the ball is being thrown to, and he runs in a straight line with speed v, and leaves 0.4 seconds after the ball is thrown. He catches it here where it's 1 metre above the beach, and we need to find the value of B. So I think things that we can do here, if I want to know how fast he's going, I know how far he travels. It would be useful to know the time, so I can work out fairly easily the time of flight of the ball. So the time of flight of the ball is going to be distance over speed, and we can do that in, distance over time. I'll get there in a minute. I was right the first time, sorry. Distance over speed, we can do that in the vertical direction. So we know that vertically, I'm talking horizontally. We know that horizontally we've got our distance of 8.92 metres. Obviously we'd keep the accurate version in our calculator from here, divided by the horizontal speed, which is 7 cos 45 degrees, and we pop that in your calculator and we end up with a time of flight of 1.8026. I've put a few extra places in there on what's needed. That means that the time of the run, if he leaves 0.4 seconds after the ball is thrown, that means that the time of the run is going to be 1.4026, etc. 0.4 seconds less, which means that his speed, assuming he can travel at a constant speed here, that's going to be distance over time, so we know it's going to be 8.92, that's the horizontal distance he has to travel, divided by 1.4026, the time that he's running for, and that comes out 6.36 metres per second. And that's the value of V then, to 3 significant figures. Okay, let's move ahead then. We have a different example here. Again, if you want to play along at home, please do pause it now and work through the question and restart when you're ready to see the explanation. We have a similar situation here where the particle's being projected from the top of the cliff again, this time at 40 metres per second, considerably faster, and it's a much higher cliff. Q is the highest point on the path of the ball, which is 12 metres above P, and it's moving freely under gravity until it hits the ground here. So the first thing we've got to do is find our angle of projection. Well, in this particular case, we've got not very much information about the horizontal direction. We don't know a distance, we don't know a time, we don't know very much at all about the horizontal displacement here. But we do know quite a lot about the vertical direction. So let's think about the vertical direction here. Vertically, we've got u equals 40 sine theta. That's the vertical component of the initial velocity. We've got a displacement of 12 metres upwards. We've got a final velocity of 0. And we know we've got an acceleration. And again, that needs to be negative because we've taken upwards as our positive direction. So using these variables that we've got here and the Suvat equation v squared equals u squared plus 2as, we end up with 0 equals 40 squared sine squared theta minus 2 times 9.8 is 19.6, so that's 2a, and s we know is 12. We can rearrange that to give us an expression for sine squared theta. So sine squared theta comes out at 0.147, and we can solve that then to give us theta is 22.5 degrees to 1 decimal place. This is a good point to practice using your calculator carefully. I would keep that value unrounded in your calculator. I've actually saved that in my memory A on my calculator, which has multiple memories. I find this a useful feature for later in the question. Talking of which, we now have to find the distance OR. This is this horizontal distance here across the bottom. Again, I'm going to call that D. Now, if we're going to find that distance in the horizontal direction, we're really going to need a time of flight, because at the moment we know a velocity in that direction, 40 cos theta, and we know the value of theta, so we can find that velocity, but we're going to need a time of flight in order to be able to find D here. Okay, so let's do that in the vertical direction again. Okay, so again we've got our initial speed, u equals 40 sine theta, and again we've got a value in our calculator now to be able to replace that. We know that the acceleration is minus 9.8, negative in the opposite direction to the initial velocity. We know that the distance is going to be minus 36, because we want it to drop to the bottom of the cliff there, and we're trying to find t. So we're going to use s equals ut plus half at squared, and substituting into there, we end up with minus 36 equals 40 sine theta times t minus 4.9, that's half a times t squared. Again, this is going to be a quadratic. It's not a particularly smiley one, but rearrange it into the classic form and we get 4.9 t squared minus 40 sine theta t minus 36 equals 0. Again, we know we want the positive version of t, so using our quadratic formula, t equals minus b, that's 40 sine theta, plus, because we want it to be positive, square root of b squared, so 40 squared sine squared theta minus 4ac, that becomes minus 4 times 4.9 times minus 36, so we get a positive in there, all divided by 2a, which in this case is going to be 9.8. Now, if you've kept your value for theta in your calculator from last time, if you've popped that into a memory, now's a good time to start using that when you're substituting into this formula. When you do substitute into this formula, you end up with a value for t, which is 4.694-ish. Again, keep that exact value in your calculator, because you've now got the information that you need in order to find d. That's going to be distance is speed times time. Horizontal speed is 40 cos theta. Again, use the theta out of your calculator memory. Multiplied by our time, 4.694. Again, use that out of your calculator memory. You should end up with a distance of 173 metres to 3 significant figures. Okay. Now, part C of this question, the speed of the ball as it hits the ground at r, this is an interesting question. There are only 3 marks for this. It is possible to do this using Suvat equations. I'm actually going to show you a different method, because I think this alternative method is much simpler in this particular case. You could, as I say, use Suvat equations to find the vertical component of the velocity, and then use Pythagoras to find the overall speed as it hits the ground at r. But I think you'll agree that energy calculations actually make this much easier. Using energy, the initial kinetic energy and gravitational potential energy are converted into, that should be an equal sign, are converted into final kinetic energy. So in the first place, a half m times 40 squared plus mgh, this is gravitational potential energy, so m times g times 36 equal to final kinetic energy, half m v squared, where v is the velocity that we're looking for. All of the masses cancel away, and out of that you should be able to find that v is 48.0 metres per second. I hope you'll agree that that's actually a much simpler, faster calculation than using constant acceleration equations in 2 directions and then using Pythagoras. Okay, so thank you for watching. As I say, the Further Maths Support Programme website has lots of information about how to work with further maths and how to support college departments, at schools and college departments in providing further maths and training for that. I hope you've enjoyed and found this useful, and perhaps you might look at some of the other videos that are available. Thanks for your time.